Bismillah ar-Rahman ar-Rahim. Dear class, Assalamu alaikum and welcome to the first lecture of week 4, and we will start from where we left in the last class. We were discussing spherical coordinate system, and we had discussed the three fundamental surfaces in spherical coordinate systems, namely r equals to constant sphere, theta equals to constant infinite cone, and phi equals to constant radial plane. Okay, then we discussed the combination of the two, r equals constant and theta equals to constant, phi equals constant and theta equals to constant, and then r equals to constant and phi equals to constant surfaces. And then at the very end we showed the three fundamental surfaces: r equals to constant, theta equals to constant, phi equals to constant on one plane, and we said that we will discuss it in the upcoming class, which is this one. So as you can see that I have drawn, we have on the same set of axes r equals to constant sphere, and this circle is just showing that this dotted circle is just showing us that this circle is not a circle, rather it's a sphere. Okay, so this is actually showing some depth into it. So we can consider that this circuit is, we should now know that this circuit is nothing but the intersection of z equals to 0 plane and r equals to constant plane. Okay, so this dotted circle is nothing but on the sphere, and it is in fact a circle, and not only on the sphere but it is also on xy plane or z equals to 0 plane. So we have also got the infinite cone, okay, which has got the radius, the angle with respect to reference axis, that is the z-axis, and we have taken an arbitrary value of 30 as an example. And then we have got the phi equals to constant radial plane, a door-like plane which starts from the z-axis and then moves all the way to the other side depending on the angle associated with it. Okay, so we had discussed already that intersection of r equals to constant sphere and theta equals to constant cone is nothing but, you know, the latitude lines on the globe. It is actually a circle, meaning the latitude, just like the latitude lines on the globe. And we also said that, we also discovered in the last class that r equals to constant and phi equals to constant, at their intersection we have got the latitude lines, sorry, the longitude lines, okay, longitudinal lines at the intersection of r equals to constant and theta equals to constant. We had latitude circles, okay, at the intersection, and at the intersection of phi equals to constant and r equals to constant we have got the longitudinal lines. But remember that these longitudinal lines are semicircles in the case of spherical coordinate systems, unlike the globe in which we have a complete circle. However, these latitude lines, okay, which is this yellow line, you can see it is actually not just a line, it is a complete circle, but I am only showing the front side of that circle, not the back side. Okay, and the third intersection was that of theta equals to constant cone and phi equals to constant radial plane, and at their intersection we had a line which starts from the origin and moves in the direction and moves along the cone actually, and it actually passes through the final point which we want to, you know, find out, and in this case is the intersection of these three curves: this blue line, this latitude circle, and this longitudinal semicircle. So at their intersection, we have got a point. So this blue line, which is the intersection of theta equals to constant and phi equals to constant, actually it starts from origin and passes through our final point, the destination point, and goes all the way to infinity. Okay, so this is how we get a point in spherical coordinate system. So any two curve, either you are given with this yellow latitudinal line or this orange longitudinal lines. If you are given these two things on a sphere, because both the lines are on the sphere, you will reach that point. Or if you are given this longitudinal line and this blue line which starts from origin and passes through the final point up to infinity, if you are given these two curves, you can get the final point by getting the intersection of this curve and this line. Okay, so you don't need all the three curves to reach your final destination. Only two are sufficient. This yellow and this orange is sufficient to reach that point, the destination point, and this blue line and this yellow circle is sufficient to reach that point. Okay, and this yellow line, this orange curve and this blue line, these two are sufficient to reach the final point. Remember that. So in terms of these curves, only two curves are sufficient to reach your final point. But remember that any of the two curves, if you take the pair, that pair is actually formed by the intersection of three fundamental planes. For example, three fundamental surfaces. For example, this semicircle is made up of phi equals to constant plane and r equals to constant sphere, while this blue line is made up of phi equals to constant plane again, but this time theta equals to constant cone. So now, although we can reach this point using these two intersection curves, but at the back end of these two intersection curves, we have got the fundamental planes, as we discussed from the very beginning, that actually in any coordinate system, there are the fundamental shapes. In three-dimensional coordinate system, we have got two-dimensional fundamental shapes, and any shape other than two-dimensional shape will be defined in terms of those fundamental shapes. Like in this case, these longitudinal lines and latitudinal lines and this blue line, all these lines and curves are being represented in terms of the fundamental shapes, and even the zeroth dimensional point is being shown in the form of the fundamental shapes of this spherical coordinate system. So enough on this. So you can see this these fundamental shapes in the figure number 15. We have I've shown all the octants, but if I just limit, for the sake of clarity and visualization, if I just limit the representation of these fundamental planes, fundamental surfaces, to the first octant, as we talked about before. So you can see that this curve is on the xz plane, this curve is on the yz plane, and this curve is on the xy plane, and these curves are nothing but the intersection of r is equals to constant spheres and the respective planes which I just talked about. So this curve, for example, is the intersection of r equals to constant and xz plane. All right. Or in other words, I can say that this curve is the intersection of r equals to constant sphere and phi equals to 0 radial plane. All right, and similarly this curve is not only the intersection of r equals to constant sphere and yz plane, but I can also say that this curve is the intersection of r is equals to constant sphere and phi equals to 90 radial plane. Okay, so because at the intersection of the radial plane and the sphere we have got these curves, always remember that. So this curve, these are the special curves. So these curves actually are showing us the limits of the first octant. Beyond these values on the left hand side of this curve and at the back of this curve or below this curve, we will get the values of y, x and z negative. So we will be in other octants, so we are not interested in that. So similarly this cone will be, you know, cut down to the a semicone or maybe a quarter cone. All right, so instead of showing the lines on the cones with, you know, with solid lines, I've shown them on with dotted lines. But remember that this dotted line is actually on the xz plane and this dotted line is on the yz plane. So never mind, but these lines are making angle theta with respect to the reference axis. Okay, so if I just measure the angle of this line which is on the cone and is actually on the yz plane, or in other words phi equals to 90 plane, if I measure the angle of this line with respect to our reference axis which is z axis, it will be theta. Okay, all right, so phi is equal to 0 radial plane is here, and phi is equal to 90 radial plane is here, but we are interested in some other intermediate radial plane because we want this point in the first octant. So the radius of this sphere is 3, the angle of this cone is 30, and the radial plane we need should make angle 60 with respect to x-axis, because radial plane is always the angle of the radial plane is always measured with respect to x-axis according to our definition of cylindrical and spherical coordinate systems. So I've shown another plane here, intermediate plane, and this plane has got the angle phi equals to 60. Okay, so at the intersection of phi equals to 60 and this sphere, we have got this orange line. Similarly, same as that one, I've just trimmed this figure to this first octant one only. Okay, so now removing all these fundamental shapes, what we'll have is the latitudinal line, the longitudinal line, and the radial line, which starts from origin, passes through the final point and goes all the way to infinity. But from now on I won't show it going up till infinity. We'll assume that it's going up till infinity, but we'll just stop it here for the sake of clarity. Okay, so if you all remove all the fundamental shapes, so we'll get the fundamental curves in spherical coordinate systems. So by the way, the fundamental curves in spherical coordinate systems is the latitudinal line, latitudinal circles centered at z-axis. Okay, on each one is on different level, different horizontal plane, just like the one I showed you in the last lecture. And another fundamental curve is the semi-circles, the longitudinal lines. Okay, the longitudinal lines which has the which has the center on the origin, but they are semi. Okay, So the open end is along the z-axis. So again, there is a hinge. They are fixed along the z-axis. If you move the radial plane left right, so they will also move left right, but these extremes will be fixed on the z-axis. And the third fundamental curve is the straight line, which always starts from origin and goes through the final point, okay, and goes up till infinity. Okay, so the beauty of, or the property, one of the most important property of this blue line, you should always remember that it always passes through the final point which we want to locate. So if I just take this length of this blue line, which starts from origin and ends at the final point, so obviously this final point is on the sphere, so the length of this line is nothing but r, that is the radius of the sphere. In this case it will be 3. So I'm not writing here, okay, but it will be 3. And this orange longitudinal line, wherever it will intersect xy plane, if we join this point to origin, so we'll get the angle phi. Okay, and this line, blue line, is making an angle theta with respect to z-axis. So I'm giving you the same thing on different pictures from different angles, so that you can appreciate what I'm trying to say here. All right, so in figure number 18, what I have done, I have shown you this figure number 15 from the top. You are standing here and you are getting or capturing perfect two-dimensional picture of this, not this, of this whole picture. Okay, so we have got xy plane. Okay, and this dotted circle is nothing but this dotted circle. Okay, so actually you are actually seeing this the radius of this sphere. So if you measure the radius of this circle, if you're looking from the top, from the z-axis, so this radius of this circle is nothing but the radius of the sphere, and this yellow line is nothing but this latitudinal circle which you got by the intersection of r equals to theta and r equals to constant and theta equals to constant. This is that circle. And obviously if you see from the top, you will see this blue line, okay, starting from origin and going up to the point of interest, and after that it will go to infinity. But as I said, after this figure I will not show that line up till infinity, so I'll stop this line here. And the rest of the thing which we'll see after this line will be this orange longitudinal curve. So this is that curve. I hope you are able to see that in orange or red. Okay, so I've drawn two lines here for a reason, and that reason is, if you are not able to see those lines, I'm just highlighting these lines. And these lines have nothing to do with the spherical coordinate system, but I have drawn it here. Okay, but before going to discuss what these lines are, I just want to ask you that what is the radius of this yellow circle, and I'm sure by now you would say that this is nothing but r sine theta, because we have already discussed about that the radius of the circles horizontal circles formed at the top of a cone, or in other words formed at the intersection of r equals to constant and theta equals to constant, is given by r sine theta. So this is this. I don't want to mess it up. All right, so dear, okay. So now this, if you see from the top, this line has got the shade on the xy plane, and this angle is with respect to that shade. So you can see that the shade of this line is on the xy plane like this. So the shade of this line, which is if z-axis is coming out of the board, so this blue line will be making some angle, but its shade is this is just below this blue line, and that shade will be making an angle phi with respect to x-axis. So why these lines? If you could just see that this line is perpendicular to this line, okay, and this line is parallel to this line. So what I've seen here, I've done here, that I've drawn these lines, and I want you to step here and see what the situation would be looking like if you stand here on xy plane. If you are standing here on the xy plane, looking this whole picture or this whole picture from here to here, when you'll see, what picture would you see? You would see a yellow line, a yellow latitudinal line, or in other words, if this is the point and I'm trying to see it from here, okay, from here, so what I will see? I will see a blue curve, blue line starting from origin. This is z-axis, okay. So actually this line is parallel to this line or this line, okay. इस line और इस line, ये दोनों lines parallel हैं. मैं यहाँ पे खड़े होके देख रहा हूँ इसको बिल्कुल, okay. So actually I am now perpendicular, I am looking perpendicular to phi equals to 60 radial plane. So if that's the case, so this line, if I am looking at the from perpendicular direction, perpendicular to what? Perpendicular to this line, and this line is making angle 60 with respect to x-axis. So this line is what? Phi equals to 60, making an angle phi equals to 60 with respect to x-axis. So now x-axis will be shifted, okay, it will be shifted 60 degrees here, so that this line will reach, will replace y-axis, and y-axis will shift further away, okay. So I hope you would be able to understand that, you will be able to perceive this. So what you will see a blue line. You're standing here and watching it, blue line starting from origin, passing through the final point and going up straight, but we are not interested after that, what happens after that. And you'll see this longitudinal curve, okay, and that curve will go beneath, but we are not interested in that. And you'll see this yellow latitude curve. This is what you will see. So this length of this blue line is r, okay. All right. So, and if you are standing here, and if you are seeing it here, if you are seeing this whole picture exactly from here, okay, you are standing on xy plane and looking the picture from here, what you'll see blue line. Just give it a thought. I cannot explain it very well, but if you'll just give it a thought, you'll see that if you see this picture from here exactly, meaning if you're standing here and seeing that picture, what you'll see a blue line, then a dot, okay, and you'll see this yellow latitudinal line, and you'll also see this orange, but I haven't drawn that. I have drawn that portion of orange which is above this point. Okay, so it will be something like this. The orange curve will be coming from this is, let's say, the final point. The orange curve will be coming from here, going down to x equals to z equals to 0 plane. So this is the final point. Okay, so I've just shown the orange curve which is above the point, which will start from this point and will reach the z-axis at this point, meaning this line is nothing but this orange line is nothing but this orange curve. Although this orange curve will go down and it will reach somewhere here, but if I would show that, I would miss this blue line, so I haven't shown that. Okay, so this is the discussion of the fundamental planes, and I've taken too much time on it, so but never mind, it was really necessary. So after a couple of minutes, I would urge you to see that and try to understand it, and after 5 or 6 minutes we just replay this lecture. Not replay from the beginning, but from where I'm leaving now, and then we'll carry on our discussion of differential surfaces, differential volume, and differential lengths. Okay, so try to recap or understand what these diagrams and the diagrams which I have presented in the previous lecture. Okay, so now let's discuss differential volume, differential surfaces, and differential length in case of a spherical coordinate system. So we'll go exactly in the same way which we used before in the spherical and the cylindrical coordinate system and the cylindrical coordinate system and the rectangular coordinate system. So we'll follow the exact order. So an exact approach. So we have got 2 points P. Coordinates are 3, 50 degrees and 30 degrees, and Q coordinates are 5 and 70 degrees and 60 degrees. Okay, so point P is shown here, point Q is shown here. So obviously now point P is on the radius is on a sphere whose radius is 3, and point Q is on the sphere whose radius is 5. So obviously and the radius of both the spheres is measured from the origin. So obviously there are 2 concentric spheres, one smaller on which P lies and one larger on which Q lies. Okay, so here we go. Here we have here we have that point P, and here we have point Q. I'm sure you're able to see it, inshallah. So if I join this point to origin, what I'll get R1, that is 3. Okay, so let me just write R1 here, R1, and this line is making angle θ1 with respect to z-axis. Okay, so now move in the direction of AX, AY, and AZ. So it means that before discussing this, we should be able to discuss the primitive unit vectors. So we have got R equals to constant surface, so for that we need AR. We have got theta equals to constant surface, so for that we have A theta. We have got phi equals to constant surface, so for that we need A phi. And you all by now know the properties of primitive unit vectors, so let's discuss that. If I see it from here, okay, and if I'm at this point, okay, and I want to move in the direction which is perpendicular to this sphere, because I want to know the direction AR, primitive unit vector. This should be perpendicular to r equals to constant sphere. If I'm at this point and I want to move in the direction in which is perpendicular to r equals to constant sphere, and if in that direction I move, only the values of r changes and theta and phi must remain fixed, and not only that r should change, but r should also increase. So these are the conditions which I must I must meet. Okay, so if I'm at this point and I want to move in such direction, so in order to keep theta and phi constant, I must move in a direction which should be on phi equals to constant and theta equals to constant planes, surfaces. Okay, and we know that the intersection of theta equals to constant and phi equals to constant is nothing but this blue line. So it means that if I move along this blue line anywhere, so theta will be constant, phi will be constant. Okay, so one thing is decided, that I must move at the intersection of theta equals to constant and phi equals to constant. Either I can move in that direction or I can move in this direction. So if I move in this direction will bring me closer to origin, meaning that the value of r will decrease. So the only direction which I am left with is this direction. If I move in this direction, theta and phi will be constant, and this direction, since is along the radial line of this sphere, so radial lines are always perpendicular to this sphere. We all know that. Okay, and if I draw a tangent on this if I draw a perpendicular on this blue line, then at this point, okay, perpendicular to this line at this point, so the line or that tangent will be that line will be tangent to the sphere. Okay, so for AR I would say that if you are at this point, move along this line, this blue line. So if we are at this point, move along this line so that this direction will be AR. Okay, so a theta, if I move in this direction, r and phi should not change. Number one, two, theta equals to constant, this a theta should be perpendicular to theta equals to constant, and it should point in a direction which is pointing in the direction of increasing values. So now if I am again at this point and I want to move such that r and phi should be the same, so it means that I should move along the intersection of r equals to constant and phi equals to constant, which in this case is this longitudinal line. Okay, so I should move along this. Moving along means I should move moving along this curve means I should move tangent to this curve. Okay, and in this direction, tangent could be in that direction, but that direction will bring me closer to z axis, so theta will decrease. Okay, so tangent to this curve means this direction, this red direction, and remember that this curve is on what? This curve is on r equals to constant sphere. So this red direction, this direction of a theta, is also tangent to the sphere, not only tangent to this curve but also tangent to the sphere. So, and this blue line or direction of AR was perpendicular to the sphere. So this blue line is perpendicular to the sphere and this red line is tangent to the sphere, meaning that AR and A theta have got an angle 90 between each other, so they are orthogonal to each other. Okay, and the phi equals to constant. If we see this picture from the top, so the phi equals to constant, this line is phi equals to constant line, so we should move in the direction which is perpendicular to this, and we already know that this direction is this. So if I try to draw it here, okay, so this see that this direction, the direction of a phi, is perpendicular to this line, which is actually the top view of phi equals to constant plane. That's why this is a phi, we already know it. So it means that this is perpendicular to this plane, and we can see that this line is also the radial line to this yellow circle, and this yellow circle is what? This yellow circle is latitudinal circles. So meaning, it means that this green line is tangent to this longitudinal this latitudinal circle, okay, circle. So if I should draw the tangent along this yellow curve, I will go, you know, a little bit in deep into this page. So it will be something like this, okay. All right, so you know, this red curve is something like this going down, but along this line going down, okay, and green a phi is going towards that. So it means that the angle between a theta and a phi is also 90. So we can say that this is 90 and this is also 90, AR and in theta also 90, this is also 90. It means that AR and A phi is also orthogonal to each other, meaning 90° out of phase, not out of phase but 90° out. So at the point of intersection, all the three fundamental surfaces are perpendicular to each other because their their associated primitive vectors are perpendicular to each other. So they are the directions, the surfaces are themselves, they are perpendicular to each other. So now carrying on the same lines, okay, now you can see again, if I change the point from here to here, okay, so the direction, if the point is here, then the direction of AR would change, then the direction of A phi would change, because direction of A phi is nothing but tangent to the latitudinal circles. So direction of tangent will be different at this point than this one, okay, and obviously the direction of A theta will also change. So you know, that was the blessing in Cartesian coordinate system, that the unit vectors were constant in direction, but in the case of spherical coordinate system and cylindrical coordinate systems, as we have seen, that the direction of primitive unit vectors, they change with respect to the point. It depends where you are standing. So now this was the case, point P on the inner sphere, point Q on the outer sphere, and this distance, obviously distance between these 2 points is r1, and now we would say that move in the direction of to reach this point, move in the direction of AR, how many units? Again, but let me just give you the picture, that point P here have got the coordinates r1. Generally I've just taken 3, 50 and 30, but generally that will be r1, theta 1, phi 1, and Q will generally have r2, theta 2 and phi 2. I hope you are able to see what I'm writing here. Yes. So, and again the relationship is something like this, that r2 is nothing but slight increment in radius, r1 plus dr, and theta 2 is nothing but a slightly wider cone, theta 1 plus d theta, and phi 1 Phi2 is nothing but phi1 plus d phi, a slightly more open door, huh? If you just take that phi equals to 2 as the radial plane, as the, if we consider the radial plane as the door, then in that case obviously what we'll have is a slightly open door in the case of q2, in the case of q. So we'll start from here in the next lecture, because the time is almost up. Okay, and inshallah the next lecture will be the final lecture of chapter number 1, and from this week inshallah we'll start the electrostatics, and we'll go in very much fast speed, because we have to cover a lot. Okay, so see you in the next lecture inshallah, and try to comprehend this all. Okay, assalamu alaikum.